So the topic is qualitative analysis, a fancy name really. Um, UA as I find it. Okay, so the qualitative as opposed to quantitative. And so the numerical analysis, the simulation and the Euler's method, that's quantitative analysis, right? The actual numbers, even though they approximate that, but you are actually know the things are more specific, even though less absolute. Okay, so specific a number, but it's not exact, but it's approximate. Here we speak in a very general, really broad terms, but nonetheless, there the answer is absolute. If that makes sense. So if we're saying it's increasing, it's increasing. Okay, so there is no ambiguity about that. Okay, so the what is exactly we're asking currently is very simple. It is the right-hand side function of our ODE. Once again, this is my ODE. Okay, the right-hand side function maybe it's autonomous or not. And we're looking at either one or two function of a variable, two functions, function of the variables. And then we speak of the domain and we speak of the regions of positive and negative values. If it reminds you of Calc 1, that is not by accident. It's a very similar analysis, even though there is way more to say, because for one in calculus, we have function of one variable, and here it is function of two variables, t and 1. Okay, so just because tangent does not have t here, right there, that does mean that we are not considering it, at least implicitly, because y is a function of t, and therefore y prime is a function of t, and therefore that question about tangent line being positive or negative, it actually affects y prime being positive or negative, and therefore increasing or decreasing behavior. Okay, so once again, just one example going all the way through. Once again, the tangent is as we're looking as it is. So the output is z, whatever the variable I made up. Depends on y, and depending on the value of y, either to be graphed like above or below the y-axis, and therefore it produces either negative or positive numbers. Everything else is a range. Positive or negative values are the only ones that will be used. We are going up and zero, so of course, plus, minus, and zero. So, so as you can see, the right away the analysis with those two things right here starts. It starts with we identify the domain, so it's undefined at pi over 2, 3 pi over 2. The tangent. So knowing functions is very helpful. It gives you a very quick shortcut where things start. And then so then my plane is then is cut into strips. Okay, each of pi, width of pi. Okay, and then in the middle of each of these strips, so these are the strips. In the middle of each of the strips, such as at pi, I'm sorry, at 0, say. That's where there's a change of sign of negative tangent, therefore the change of y prime from positive to negative. Okay, so that's the initial analysis. The once again zeros. Those red dots are where the function is undefined. This is where it is equal to 0. Okay, so these are the points where it is equal to 0. And so these are the most important points. Now we tilt it. Okay, we tilt it in order to sketch very roughly our solutions. Well, the solution set is what we're after, rather than one at a time. A sketch of a solution set, a portrait. Very, it's not a photographic portrait, but rather a drawing, a very crude drawing, almost a caricature. Okay, so once again, positive and negative, as you can see, the picture is very clear here. Now I tilt it to the picture that we saw above. Now it's on the left, and it is tilted so that y is now vertical. Why so? Because this is where our interest is, where things are happening. So the t-axis and the y-axis, that's our interest, that's where the graphs lie. Okay, so that's why, for convenience, I tilt, I rotate the YZ plane right here. I rotate it in that direction. Okay, so then the y-axis are allowed. And once again, I erase this. This one is all gone. That's not, doesn't matter. This is what what I keep. Okay, so plus minus 0, that's undefined. So there is the fourth possibility actually. So the green is 0. Okay, greens are zeros, the values of of my function zero, that's 0, okay? Then the pink one is actually undefined, remember? So it's undefined, a circle, undefined. And then the rest are plus and minus, okay? So then with that information, I could actually take a moment. An important point to be made is that even though the graphs are as y depends on t, these are my solutions. So the solutions will be here. Nonetheless, the whole problem is one dimensional. It is a pipe. Keep that in mind. So t is the second variable on which everything depends, but the motion, the dynamics is actually entirely one dimensional. So we are flowing, that's right here, flowing forward or backwards. That's it. So either there might be no flow in the where the function is undefined, the flowing in the forward, flowing backwards, or stationary where there is nothing is happening. Okay, so I classify those points where everything is separated into the stationary points. So there's nothing happening there, is undefined, where there is no flow. Okay, so and then plus we'll look at it where I have 0 in green, the solution is stationary. Then wherever is plus is going up. Very crude picture, right? What's on the right, and then negative it goes down. Okay, so that's the match between plus and minus on the left and zeros. And the pictures on the right, the illustration to be discussed later, the pipe. So this is my pipe right here. Okay. So that is already is quite a lot of this. This is the portrait. Okay, a caricature. Look at it. You know the graphs do not look like this. They're not straight lines. But since we don't know which way they behave, at this point we can just as well say that's the way it goes. And so I drew it as straight. Okay. So okay, so then there are questions to be asked if we want to make it a little bit better. The question we ask about the relation between those sloped curves and those lines, the green line and the red line. What about the green line and the red line? What that solution? It seems like it's going up, right, towards right here. It's going towards the green line. What is it? What's the effect of that? It's going on and it goes towards it, and then what? That particular solution, it's increasing, right? Okay, and then so I drew only one very sketchy line, but then one long term. What's the long term behavior?
It's stationary.
Well, are you saying it will become stationary?
Yeah.
So this is becomes so exactly stationary or approximately stationary. Okay, exactly. This is exactly. Okay. So in other words, it is actually what this is called frequently. This situation is called a sink. Okay, so it's like a flowing into that spot, and so then you would say that it is that picture which I drew on the right is exactly what we expect to happen if it is a sink. So the water flows and then falls into the sink. There's only one problem. What?
It will never reach because it's an asymptote.
Well, you're saying it's an S, but why? What's wrong with the picture? Picture I drew here.
It's touching.
What?
That's touching a lot.
Well, is it touching? So no, it is becomes, so it's not, it is touching the line. Okay, so what's wrong with that?
It won't touch that line. It
What?
won't touch it. Like it's because it's fast.
Well, you have an alternative interpretation, which we'll get to. So let's decide why this might be problematic. What's wrong with this interpretation? The picture, you've seen this picture before.
It's not unique.
Not unique, right, exactly, that's not unique. So if we can claim uniqueness, then that cannot happen. This is not unique. Okay, so merging of solutions is not allowed. So that, so we'll quick look back. The equation is tangent a function is differentiable, so we have uniqueness everywhere the change is defined. We're going to have uniqueness, and so since the stationary solution is a solution, and the other one cannot merge with it in the exact way. So you can't say it's still a valid alternative solution that had been proposed already, that it becomes stationary approximately. And another way to put it is to say that it's asymptotic, right? So then the alternative interpretation is this. So the horizontal solution remains. So it's a sink. It's not a sink. It is what do you call it? The water is standing there. Okay, but the water that flows towards it never actually falls into the sink because of the uniqueness. It looks very much. Look at the picture. In our pipe, like everything goes towards it, looks like a sink. And incidentally, then and so we have a bunch of sinks here. But the reality of a differential equation that it only can approach it asymptotically. We don't really have a choice. So it is increasing to begin with, but it never reaches it. These are two facts once again. So we're not guessing here. They're only that's the second one is the only. Once we reject this. So if this is no, then this is definitely a yes, because there is no other way for it to happen. So it's increasing, and then it is merges. Well, actually, there's the third yes. There's the third possibility here, just below, to be seen. So it seems like there is no third possibility, but there is actually a third possibility. So it cannot merge, but and it approaches it, but can it approach it in some other way? There is a way, but let's nonetheless make sure that that's the key question. That's the key question, because once we understand one solution actually being repeated everywhere else, it's the same solution because the behavior is repetitive, it's tangent, so it's periodic this way, and then the whole equation is autonomous, so it repeats itself in the horizontal direction as well. So that it means that really understanding one solution will solve the problem. So okay, so we reject the merging and we accept asymptotic behavior, and then there is a third possibility. But before we do that, what about on the other end? On the other end, okay, so let me look at the picture. Here it is. Yeah, this is the other possibility, by the way. So this is the possibility that we claim to be on the right, but this is another possibility. Also, it is increasing, but it actually merges into the curve. Okay, so it is possible. So we only rejecting it with by looking at a more subtle analysis. So we take this one and this is not it. Okay. So anyways, but so how do I know this? Because the derivative goes to infinity. Okay, the derivative goes to infinity, which is not the case in the case when it approaches stationary solution. Say, for example, if I specifically look at the green light, how about then I take the x-axis 0? Okay, so say this let's suppose we investigate in this one. So what's the behavior like? And the answer is, what about the derivative? So it's not y, it's y prime. So what is the limit, not of y, but of y prime, as we are approaching the x-axis? And the answer is, what's tangent of 0? Tangent of 0 is 0. So in other words, yeah, like I said, tangent of 0 is 0. So y prime then is approaching 0. It flattens out in the horizontal direction. That's why we reject this possibility on the left. Okay. To begin with, and secondly, is for us to worry about. So that's on one end of our solution. At the other end is how to approach the pink line where the function is undefined. Okay. So, and that's the story is the opposite, right? So for example, if once again I take this one or that one, the red ones, tangent of pi over 2 is plus infinity. And so which means that our derivative is plus infinity. So this is actually yes. Okay, so actually I think I messed up the curves here, the colors. This is the green line where the stationary solution such as y equal 0. And this one is undefined. such as y equal pi/. Okay, well. Let me correct myself. So the actual picture looks like. Okay. So it's on the other end. It's on the other end. Okay, so once again, if I look at this picture, the one that I have here, in blue, the one end is how to purchase the y equals 0, and the answer is asymptotically, the green line, this is also the green line. Okay, so this is a y equals 0. But on the other end of that same solution, how does it approach the pink line where the function is undefined? And the answer is in this fancy way. So actually does this. So it grows fast and then it flattens out. That's our solution. So once we understand that, then there is some argument to be produced about that. This is I draw one copy. I drew one copy, say maybe this one. I draw one of them and then I copy it as many times as necessary because they're very big difference. So once again, it leaves the red curve without touching it because it never crosses the undefined there, goes up fast, then flattens out and asymptotically approaches the sink, or the horizontal stationary solution. Okay, so once again, having one and then just copy many times as necessary, and then that's the portrait, which is slightly better than the crude caricature that we have here. So yeah, I have to call it a caricature. And this is a more reasonable. It's still not a photograph. It's a drawing, but just more reasonable. Okay, more to the truth. Some more subtle ideas that have been used. So this is okay. We only look at plus or minus behavior, and here we take into account some more subtle things such as uniqueness too, and as well as limits. Okay, so these are the limits that we have. Okay, and then we do it, if you are convinced with that, do it drawing with the Euler's method. Okay, so the y, you remember the Euler method, you don't start with it because you don't know where things break down. If you know where they break down in the middle, then you stay away from this because where the function is undefined, that's the way you have division by 0. If you get close, you divide by a number that is very small, then you end up with infinities and all kinds of wild behavior will be produced by the Euler's method. Okay, so that's the portrait, which is, this one is both qualitative and quantitative, and we did it carefully so you can see how it behaved nicely. Stationary in the orange, and then function approach it in the from below. Okay, without crossing. So that's the Euler method won't tell you that they cannot cross. That orange line is not being crossed. Either direction. Okay, any questions about this analysis? So it remains to just do this a few times to get used to it. So I'll just show you a couple of quick examples of how that happens. But this is the outline. So look at the zeros of the derivative. Once again, calculus 1, as well as the point where it is undefined. Okay, so the function which is the derivative is undefined, and look at between those points, the sign of the function does not change. If it is continuous, therefore monotonous, they will not change. So either plus or minus, therefore my solutions will be either all going up or all going down. Okay, solution, that's what they call it for analysis, is confirmed with Euler's method. Here's another example. This one has certain non-differentiability, but still autonomous. And so once again, here all I do is the arrows. Once again, which I just know which one is going. And then I classify, sometimes make sense to classify each point, each stationary point as either the sink, everything goes towards it, or source, everything comes out of it, or path that it appears, but it's not really the case. So this is I call it a path, but really only because there is some water is approaching from one direction, and then it moves away on the other side of that dot, and that it gives you appearance that it goes through, but we know that it cannot because of the uniqueness. So once again, the stationary solution cannot be crossed by other solutions. So that proves the asymptotic behavior, and that once again with Euler's method. Okay. Okay, I'll skip on non-autonomous. so this is optional. It's on non-autonomous, just instead of having one solution to be copied a lot of times, the behavior might be more complex, but still, the function is very simple, as you can see, and then we cut the graph, we cut the ty plane into two halves, and then all functions are decreasing on the left of the red line, and all of them are increasing on the right. And it takes some time to figure out how it is even possible, but as you can see this. Okay, so more another one, the behaviors might be very complex. This one is very simple, but you look at them, it's quite an interesting kind of behavior. There's only one. It's not a stationary solution, but it is a solution that is straight. Okay, so there's one straight line, and so that's if you were to analyze something in a qualitative fashion, you look for simple solutions such as stationary solutions and maybe straight lines. So that's actually the differential equation actually has constant, not a constant, but linear solution, which is with the right formula right there in the middle. Okay, so that's what it is. Discontinuity. What does discontinuity do to our solution? We cannot rely on uniqueness. That's the only problem. And also you can see the abrupt change of the direction. So but still continuity, and so the computer catches that very easily. So these are weak solutions, right? So which Euler's methods won't be able to tell apart. So they are not differentiable. They're not differentiable because, well, all those corners. Okay, so on a more so that's an ad hoc, if you like, way of doing things. So you extract very basic information, and then maybe some more subtle things can also be discovered using uniqueness, using differentiability, using second derivative, possibly using limits. Okay, so everything from calculus 1 comes up as needed. So let's look something in a way more basic way, and which is really will be very simple, but it will become more simple as once we get to high dimensions. So what follows becomes only more complex once we go to the next high dimension situation. So these are remember we did the analysis of curves apart from differential equation. The solution set might look like this, and then what if we zoom in on it? What happens? They look straight. Not only each solution looks straight. Together they look straight, so they flow. That's a flow, a potential flows, and they are virtually identical to each other. Okay, so once again reminds calculus 1. We zoom in on a differential function, it looks straight. But here we zoom in on the family of curves, but the effect is the same. We have a bunch of parallel straight lines. Okay, so we call it generic behavior. Very, very simple. So there is nothing about the solution set in that location that to be discovered. However, what is different is actually we already noticed that the stationary solutions are interesting. They seem to be the simplest ones, but they're in the vicinity of a stationary solution. There might be different behaviors: sink, source, and pass. Okay, so that's surprisingly we turn everything upside down and we concentrate on points where the behavior there is nothing is happening seemingly, but in the vicinity something is happening. So once again, this point is simple, but if I zoom in on over here, for example, that will have a different effect. So we have solutions approaching from both directions here, but on the other hand, over here they may be running away from it. It depends on whether it's autonomous or not. So that's the generic. We're looking at autonomous differential equation, and then once again it's canal or a pipe with a flow that does not depend on the dynamics, does not depend on time, and so there is no T over there. The flows might look like this, and once again the three main the main situations are either everything is generic, or something, there is a stationary solution there. If there is a stationary solution, then in its vicinity, the behavior might vary. Okay, so if I concentrate, as once again, let me make that clear. If I pick this one and then look at all the behavior in the vicinity of that arrow, you will see exactly the same arrows. So all same. If you zoom in on one generic solution, the vicinity, you still have all generic. However, if you zoom in on a stationary solution, that's not the case. right? So it is stationary, but in the vicinity of that point, the behavior is not stationary, right? So once again, you can have sink, source, or pass. Okay, so we will be, I'm plotting arrows here on purpose because, once again, keeping an eye on the possibility of higher dimensions, we speak of vector fields. So vector fields, and so these just happens to be one-dimensional vector. Okay, so once we get to two-dimensional vectors, the vector language becomes indispensable. So once again, so suppose we're looking at the single point. Okay, so and then one point in time, that's what local analysis is. Zoom in on every point on the y-axis, one at a time, and there are two possibilities: either the derivative is not equal to zero, or it is. Okay, if it's not equal to zero, especially when the function is continuous, then it's either it's positive or it's negative. Okay, and in the vicinity of that point, once again, it's either positive or negative, right? Remember that the argument about continuity, if you have a continuous function and it passes through this point, in the vicinity, it will be either entirely above the x-axis or entirely below the x-axis, which means that the behavior does not change. And therefore, the my function, the right-hand side function, my one-dimensional vector field will be all positive, and therefore all of the solutions will be going in the exact same direction. Okay, so that's the as easy as it gets. So my this is my y right here. That's my point y, and then at point y, the derivative is hold on a second. So this is actually two different examples. Okay, so whenever the derivative is the right-hand side of my differential equation, whenever it is positive, we have all the function growing. When it's negative, the full function are decreasing. Okay, and once again, if you zoom in on one function in the vicinity, all the graphs look exactly the same, straight lines going all up or all down. That's the generic situation. Now, non-generic, and it's in fact the word frequently used is singular, is when the derivative is equal to zero. Okay, so then that's where the behavior might change. Once again, calculus one. How can you change from decreasing to increasing behavior? Well, you got to hit zero. Okay, so derivative has got to hit zero, and so that's where we are. And so once again, it is stationary solution is assumed to be there. That's it. But that's one point. What about the vicinity? And the answer is like this. So once again, derivative at that point is equal to zero, and then you have four possibilities. That's the sink. Above it, my function is negative, and everything is going down, right? Well, this is a good picture. This is my pipe, right? This is my pipe, and then above it, everything is going down. Below, everything goes up, and then it would have a sink. Okay, so once again, keeping in mind, this is a very crude picture here. These are the graphs, something more specific, but nonetheless, that one-dimensional picture is the most revealing, and except for that idea that about asymptotics, it does not cross. It does not. No liquid falls into the sink. Okay, so let's sink. Once again, sink. Okay, and then so what else can happen? You can have the opposite. Naturally, you can have negative here, positive there. No, wait a minute. The second possibility is this. So positive above, negative below, which means that it falls away from it. Okay, so once again, this is my pipe, and everything goes away, and then we call it the source. Once again, not literally, because there's nothing, no liquid leaves that spot because of the uniqueness. So no water leaves. Same. And here, no water falls into it. Okay, so and then the third possibility is, so as you can see, the sign changes. So from positive to negative, for negative to positive, then we respectively have sink and source. And then the third possibility is when they have the same sign on both sides, either both positive, both negative. Okay, so like this, positive, positive. Then, as you can see, the behavior on the left and the right is the same, or rather below and above that point is the same. So it gives you the appearance of passing through that point, and once again, no order crosses the, that point, but we know what happens, it's just gradually approaching, asymptotically approaching that particular point. That's what the picture is supposed to show, that the asymptotic behavior here. Right here. This is asymptotic right here. Okay. So, so very simple analysis, subtle things are thrown out. So the only thing we really take into account are, like I said, the sign of the right hand side function f, and then the conclusions are very broad, but absolute in terms of in classification. So this is an unambiguous classification of the behavior of a autonomous ordinary differential equation in the vicinity of 0. Okay, so once again, assuming continuity and well, actually, probably well, let's say continuity of the right hand side function f, we have asymptotic behavior, which we have the 3 possibilities, and and that's it. And so classification is complete. There is nothing else that can happen. That's the great thing about classification. Then that's all there is. Okay. So it's called a classification of equilibrium, and once again, you have only 3. And why it's so simple? Because dimension is 1, and once we move from pipe to what, like a pond with complex motion, a pond, 2-dimensional pond, then that behavior will by far exceeds the this simple analysis of only 3 possibilities. So stable equilibrium means that, means what does stable equilibrium mean? Because if, so first of all, it is an equilibrium. So if you are in the 0 source or sink, you're not going anywhere, right? So that's the equilibrium. What makes it stable or unstable? In what sense? It cannot leave it. So what's so stable about it? This classification again. Okay, so do I have an explanation here? I mean, I guess not, but what makes this stable and that one unstable?
Everything's going to one point and the other one, everything's diverging away from the second one.
Yeah, but so this is true, but what does that description have to do with stability? Consider other equilibrium. Think about equilibrium, not in a pipe, but in a kind of, when does that come up? Equilibrium. What does that do? Equilibrium. What?
Something that rests.
Yes. Right. But now can you think about what make that rest vary in terms of being stable or unstable?
Anything that acts on it makes everything equal, so it's like it all cancels out.
Well, you're right. No, not that it literally cancels, but it will be brought back in a way. So the best example of equilibrium is this. Okay, so if you move the first one, it's on a hill, totally stable. But if you move it a little bit, or you place it there, but a little bit off the center, or it's not exact, then it will roll away. Okay. On the other hand, if you are even off a little bit with that trope, then it's okay. It still will be there. It will not go anywhere. Okay, so it might oscillate or something, but certainly will not roll away.
So it kind of has something to do with like everything relative around it. So like if it's like you're slightly different, it'll kind of
yeah, so it could be computation too. Think about computation. So if you are computing and then you are off by a little, where do I place it so it will be in equilibrium? If you are off by a little, you might be in big trouble. So if you're designing any kind of system, then naturally you want a stable equilibrium. So that once again, the errors are inevitable in computations or in placement. They are measurements, computations, whatever, produce errors, and then the stable equilibrium will assure that at least if it is you're off, at least that's how much off you are, and you'll stay off by this much. It will not explode in your face. So that's unstable. Okay, so anyway, we'll get to that when dimension is 2 shortly. We have one more last topic for dimension 1, and that is, it's a big one. It's called linearization. Okay, so we already did one linearization. Remember when we did linearization? Linearization anyway. Well, yes, but in a particular way, right? So linear referring to the linear line as well as linear function. So what does calculus have to do with the linearization? Well, doesn't matter because we are not doing that. We're doing different linearization. So the previous linearization was in the, okay, first this is the review. So, okay, so once again, let's review this, the overview of what has happened so far. Ordinary differential equation, algebraic solutions, very limited number of things that we can try, separation of variables, substitution, theoretical analysis, existence and uniqueness, numerical analysis, Euler's method, qualitative method analysis is increasing, decreasing behavior, as well as you can probably derive concavity as well. Okay, so the idea is simplification. Okay, simplification of what? Of the differential equation itself. None of its solutions. This is a simplification, right, in a way, but nothing happens to the differential equation. You just go backwards and find what your model was in the first place, and then the solutions are simplified. Instead of having a continuous curve, you make it the bunch of dots, and they approximate the continuous solution somehow. This is simplification of the differential equation itself. In other words, that f. So y prime is equal to f of y. So what do you can simplify y, okay, or you can simplify f. Okay. By f, yeah. And the simplification has to be fair, and we replace it, we linearize it. Non-linear function is replaced with a linear function. That is calculus 1. It is the tangent line again. And just to remind you that y prime is equal to ky. That's a linear one. We have solved this problem. Remember this one? This f is linear. This is my f, and it is linear. And it is solved. The linear differential equation has been solved once and for all. Remember, they produces the exponential function. Okay, so if we can in a justified, careful, and thorough, a very careful way, replace our f with its linear approximation, then we're done because that one has been solved already. Okay, so that's the big idea. Simplification, that is simplification. We're in this one. So from here to there. So this is the general one, and we replace it with fy, we replace it with ky, which is way simpler, and the solution is exponential. Okay. So okay, so Euler's method approximates the solutions by linearizing them one point at a time, and that's why you jump. And here we linearize the differential equation itself. Okay, so once again, if we take these side by side, we did a little bit of that, and so we linearize y. That's the, well, let me maybe number these. So this is number 1, Euler's method, and this is number 2, actual linearization. This is 1. Okay, so but the mathematics for both of them comes from the same place. That's calculus 1. The end of not the end necessarily, but finding the tangent line. That is linearization. Finding the tangent line, oh no, it is a fancy word, but it is only sounds fancy because it's only seems unnecessarily complicated in dimension one. Once you go to higher dimensions, the linearization, which is calculus one task, becomes way more complicated. Okay, so let's just enjoy as long as we can with this one-dimensional situation. So once again, Euler's method on the left, linearization of the differential equation on the right. So we linearize y, the unknown function, replace it with an approximated solution, which happens to be linear. Okay, and here we approximate the differential equation, replacing f with a linear function. Okay, so then this is my linearization on the left. Y is this is the initial where we are. This is the time, and then this is literally the tangent line. Tangent line with a known derivative, okay, and known point. Known point. So we're solving an initial value problem every time with a known derivative and known value, but we just assume that that one single value of our function over there comes into play. We plug in, as you can see, this we plug in. Y is equal to y of a. So if we know where we are, we know the value of y, we know the value of f as well, and that gives us the slope of our line, and that gives us one step of our Euler's method. This is one step of Euler's. Okay, just to refresh your memory, and then very different on the right, as you can see what happens. So my function f is replaced. So y prime is this is the original. Okay, and then instead of f, I have L. Literally, so f is replaced with L, and I just want to simplify it in a matter that is justifiable, and that is we have a linear function, and then once again that one is just solved by analytically, right? So that problem has been solved, and here we just repeat it as many times as is necessary. So that's the Euler's method on the left. Okay, so then also this is done. This is we know how. So everything, all the pieces are already known. We know how to linearize. That's the same as find the tangent line of the function, and then we know how to solve the the differential equation as well. So it's just something that you saw in calculus one, just comes in a more in an environment that is new. Okay, so we have to do that from scratch. Okay, so once again, we convert, we turn towards the letter only. So why? Let's look at a simple example. That's a whole example right here. It illustrates that what we're doing. So y prime is equal to sine y. Linearize at 0. Here you have to know that a linear approximation of sine y is equal to y. Anybody remembers y and how? Sine y at 0. What does it look like? What's the derivative? Derivative of sine is cosine at 0. Cosine is equal to 1, which means that that your tangent line is y equals t. I'm sorry, y. It's not even a y. It's like z is equal to 1. That's the tangent. Okay, so once again, the picture is probably more helpful like this. This is my sine, and this is the tangent line. And so you can see the whole point of the tangent line. If you zoom in, then the distinction between the curve and the straight line disappears. Okay, and so that's exactly what has happened in a very abbreviated way. So sine y is replaced with y, and that's whether you do in physics or engineering, or that's such a common thing actually to do. That just sine is complicated, y is not. So let's replace sine y with y. But that's why we do it. Because it's simpler, but why we pick y, not something else? Because y is the tangent line to our line. So once again, this is y, and this is z. Okay. So approximation. Then once we replace a complex differential equation with a simpler one, it is solvable. Okay. So the answer is right there. The bunch of exponential functions. So what remains here is to practice somewhere, that's the reason, sine y prime, at y equals 0 is equal to 1. We have to practice linearization. The letter part is not complicated. And they give some background why it works out and what is that we're trying to accomplish here. Because think about it, we replace our differential equation with another one. Okay, so well, why not replace it with something simpler? Why do I pick y equal, why do I pick this one? I have to think of simpler equations. So why is this justifiable in the first place, and why it is good enough? So in what does it mean to be good enough for such a replacement? And the answer is actually is qualitative analysis. Okay, so we want the qualitative analysis to be the same. That's the main idea. So as we are often unable to solve a differential equation, we encounter, let's try to replace it with a simple one that can be solved. We know how to solve it. Okay. So actually, to understand how it works out, we will try both constant approximation and linear approximation. That's anyway, you need to do it anyway. And then the purpose and what we're trying to accomplish is this: we want the new differential equation to have the same qualitative behavior as the original one in the vicinity of that point. So literally, if it was sine y over y, it's not really, we're not replacing the whole thing. We are concentrating on it at y equals 0. So one particular, if not point, it is a strip of, but it is really one point on in that what's happening. So suppose your dynamics of in your pipe is described by this little differential equation. Looks simple, but really not that simple to solve. And you concentrate on one point at a time, and you want to know, pretty much decide what's happening at y is equal to 0. There are three possibilities. Remember, so once again, sink, source, and a pass. Okay, which one is it? Okay, so when we're replacing it, that one should be the same answer. So the original one and the new one should have the same answer about the classification of that special point. And so if it produces something else, then our simplification is excessive. It gives us a differential equation that has nothing to do with the original. Okay, so at the very least, we require this to be the same. Okay, so it's very simple to do sometimes, and sometimes it's slightly more complicated. But in one dimension one, it is totally manageable. Okay, so let's start with constant approximation just to make that case why we're going this route. As you can see, y prime is equal to y instead of why not y prime is equal to 1. It's simpler. Why not y prime is equal to 1 or 0 for that matter? Well, here it is. Okay, so let's take this differential equation that's nonlinear. I picked y squared is equal to y prime is equal to y prime is equal to y squared. Okay, so we know that the solutions are it is actually solvable. So as an example, so we produce a bunch of hyperbolas. Okay, so I separate variables. I integrate. I have y depends on x as a reciprocal. So we have a bunch of hyperbolas. And then if we try to classify the behavior, the two main behaviors are either the pink or the yellow. And once again, generic behavior is pink. Everything is going up, and then in the vicinity of a stationary point, the behavior might vary, and so that's where might be interested in. So if we pick the pink one, y equal to 1, so y is the vertical axis, by the way, here. Okay, so if we pick in the vicinity of y equal 1 here, then indeed the stationary or constant approximation is sufficient. Y squared at y equal to 1 is equal to 1. That's the constant function that we can take. And we can take our differential equation here and replace it, as I promised. This sounds silly, but with this one. Okay, y prime is equal to 1. So way simpler. Seems very too simple, but the reality is it gives us all we want. It gives us what? Gives us this. If y prime is equal to 1, this is, hold on a second, what letter do I use here? X. I'm still using X. Okay, so I probably need to make up my mind about the name of the variable. Okay, so let's go back and call it t. So this is t, this is t, this is t, this is t axis. Okay, so constant approximation, So this is y and t, okay, and here I switch to x again. So, okay, so it's fine, it works out. It works out, y prime is equal to y squared. When replaced with a new equation or way simpler, it produces the behavior that we expect. They look like this, right? Y equal x plus c. I integrated here, right? Y prime is equal to 1 means that y is equal to x plus c, t plus c rather. And so all the equation, all these solutions look like this. They increase. So whatever's happening in pink there, we have captured with this very simple approximation. But now, if we try the same to pull the same thing at the yellow point where y is equal to 0, then it's not going to work out as easily. Okay, even though it's so this one works out, even though these are definitely straight lines, not parabolas, hyperbolas rather. But nonetheless, the qualitative behavior is the same. Okay, so it works out. But if we try now to pull the same trick with the in the yellow area, it does not work out anymore as well. So y is equal to 0 now. So this is yellow. Okay, so constant approximation of y squared is 0. Once again, I plug in y equals 0 into my right hand side y squared, I end up with 0. So my new differential equation is this. That's my simplification. Okay, so what's the solution of this differential equation? Y prime equals 0. Let's solve it.
I equals C.
Y equals c. That's right. So that's it. So it's a bunch of straight lines, and that is not good because it does not match our behavior. Right here in yellow, there is increasing on the left and increasing on the right. This actually happens to be pass, right? It goes this way and then that way. Our approximation does not reproduce that effect. We have actually a kind of a bunch of stationary points. That's what we have produced. Every point in the vicinity of 0 of this differential equation is stationary. So that's not what we have. So the qualitative behavior has been changed, and therefore we lost information, and our classification has failed. Our simplification has failed because our classification does not match the original. So that's the problem, and that's why we have to do something else. Unfortunately, that's where we move on from constant approximation to linear approximation. As an example, has nothing to do with ODE, is square root of 4, square root of 4.1, say, is approximately equal to square root of 4, which is 2. Okay, so that's constant approximation. Okay, so that's best you can do, right? So 4.1, you don't know how to compute square root. What do? You find a constant that lies nearby, that the square root of which you know that square root of 4 is 2. So that your replacement of you're trying to understand how square root works. You replace it with a bunch of constant functions like this. Okay, so so whatever number is, as long as you're fairly close to 4, you pick 4, and the answer will be 2 every time. So that's constant, literally. If you are looking for a more accurate approximation, especially in continuity, then instead of constant approximation, you do linear approximation. That's where you need the tangent line. Okay, so that's roughly how one would expect, how one would design a calculator. See what I'm saying? The calculator, how do you design a button on the calculator that has square root on it? Well, not like this. This is very crude, right? So I point 4.1, I give me 2. I type 4.2, it's still 2. 4.5, it's still 2. Well, certainly not. That's not how a calculator works. But so if you want a more accurate, then you move on from constant approximation to linear approximation. Okay, and then the accuracy goes up by a lot. So that if you want to review that, that is worthwhile. And we failed for a different reason. As you can see, the qualitative behavior has been lost. So okay, so then let's carry out the plan that we had, but this time we do linear approximation. Okay, so Yeah, so that's the outline of what has happened and how it might fail, even though the solution is, as you can see, is straightforward. This is a differential equation that we start with, this one, second, this one is replaced with that one. So one single value, look at it, f of y on the left, f of a on the right. So one single value of y is plugged in, and then the right-hand side become constant, and once it's constant, its solution is written very easily, right? So it's a bunch of linear functions. Okay, so okay, but then as we can see, we have failed. So and we failed specifically in the particular case. Nothing wrong with whenever the f is not equal to 0, we are getting the correct qualitative behavior. But when it is equal to 0, we do not. Because if the function at that point is equal to 0, then we have a bunch of constant stationary solutions. So this is a no. So it is, like I said, it is in fact those special points. They are truly special. We have to have a better method to understand what's happening in the vicinity of that point. And the answer is, as I said, to linearize. Okay, so once again, that's the behavior. Original function on the left, linearized function on the right, matches there. So there is no trouble whatsoever. That's the constant approximation. As long as the f of a is not equal to 0, we have it, and so we don't have to do anything else. So that generic behavior is captured by a constant, no matter what that constant is. Okay, so whenever the function is positive, then we have increasing behavior. Negative, we have decreasing behavior. There is nothing else that can happen. So this is where it fails. Okay, so once again, in the middle of the function is equal to 0. Above it might be positive or negative. Below it might be positive or negative. The behavior might be like this, like this. But the answer is a simplified function produces a bunch of constant solutions that there is no match, and so we have to throw it out for this particular case. And we're not throwing it out, but rather we are going up in one step up, right? So from constant to linear, and if it fails again, the next step will be what? Constant linear. What's the next one? Quadratic, right? Quadratic cubic. Remember, calculus 2, Taylor polynomials. So different ways to approximate your function, and here we're not going beyond the linear. So okay, so let's do that. So I'm picking a different function, y prime is equal to y squared plus y in the vicinity of y equal 1. And I evaluated at the point of 0, at point 1, okay, the value of the function is equal to 2. If I were to replace it with y prime is equal to 2, I have a bunch of increasing functions, which is fine. It approximates well, but if we now move to the different location, y is equal to 0, then the right-hand side is equal to 0. Okay, and therefore replacing it with our differential equation with y prime is equal to 0, once again fails for third time already, produces a bunch of constant solutions. So what do we do instead? We do a linear approximation. So that's really what the answer is. So instead of plugging in the value of y equals 0 at the top, what do? I plug in the value. I keep this. I'm still going to need it for my linear approximation. But I plug in. I evaluate the derivative, and then I plug in 0. Okay, so that's the differentiation here. Y squared plus y is equal to differentiated, gives me 2y plus 1. I plug in y equals 0, and the answer it gives me 1. Okay, so what's the linearization? Derivative is equal to 1. What's the linearization? It's 1. 1 times y. That's the tangent line. So my derivative, one single value of derivative becomes the slope of my straight line. Okay, so that 1 is the derivative of the slope, and this is the tangent line. So y squared plus y is a parabola, and this is what we have found. Y equal 1. I'm sorry, that's not the y. This is the c is equal to y. Okay, and this is the original curve is y squared plus y. So z is equal to y squared plus y is a parabola, and then at one particular point right here, y equals 0 here, it's the y-axis, and then we replace our parabola with straight line, and then we ended up with to be confirmed, a valid approximation. This is my new differential equation. Okay, so instead of one that is right in the beginning, this one, okay, complicated somewhat. I replaced with a simpler one because it's a linear now, and solutions already is available in our, it's in our hands. Okay. And then once again, what is so special about that behavior is, I have a picture here, not have a picture here, so C, so it's this is general, the picture, we already solved this a few times. So that's my qualitative behavior, and it matches, supposed to match. So that's certainly, we cannot, I don't want to solve this equation and then confirm and then compare it with linearize and say it's the same. We already did that once, but here we have actually need a theorem to justify this method. So I here, well, I'm not sure why this still unjustified, but what I'm saying here to why that method is good, because the qualitative behavior of the new differential equation matches the old differential equation. Okay, so if it is the case, then we're fully justified doing exactly that. Okay, so just at this point, I could certainly try to justify by qualitative analysis, right? So, well, what is it? Okay, so let me carry out a quick qualitative analysis of this. So to confirm our theorem, so these are y's. Okay, so this is equal to 0 at 1 and -1, right? 1, I'm sorry, 0 and -1, 0 and -1. So this thing is equal to 0 at 0 to 0 and at -1 is also. Okay, so this is what the parabola looks like, right? So so this -1, this is 0, and then we have plus, minus, and plus. Okay, so which means that my solutions will be in the vicinity of 0, which is our only interest of this. Okay, so what's the behavior? So if I draw like this, so let's go horizontal now. If I did this is y equals 0, what will the solution look like in the vicinity? If I'm below the y-axis, what do they look like? Up or down? Down of the minus sign, right? Like this. And above, it's a plus, so. Okay, so that's a quick qualitative analysis of my differential equation, and indeed, now if you compare this to what we have built from linearization, it matches. Okay, so confirming this indeed true. Qualitative analysis of the new differential equation matches that of the original. Okay. So linearization sometimes are quick, as you can see. This here's some of them are well known. Sine is replaced with y at 0. Cosine is replaced with 0. Okay, at 0. So because it crosses the y-axis horizontally, or in this case, z-axis. Okay, so in general case, once again, that's the idea. You can actually once again, if you have this this is the problematic situation when the derivative is equal to 0. So we only address that. So f of 0 is equal to 0, and our interest is in the vicinity of 0. So a constant approximation will not do. And so what do we do then? We compute the derivative of f. And then this is my new differential equation. Look at it. So f prime of 0, which happens to be just a number, and this is a linear equation. It's not just linearized, it's linear. Okay, because it's nothing but multiplication. If prime of 0 is the number multiplied by y, and the solution can be written at once like this. Okay, so that's the solution. The solutions right away, right there. So one single number in the exponent, and then multiplied by t. So a bunch of exponential functions, which I drew just a minute ago, and then you're done. Okay, so at least the qualitative analysis is there, very easy to detect. Okay, so yeah.
So procedurally, we find the zeros of the original function f.
Yes.
And then we take the
Yes.
derivative of that function f.
At those points.
And then substitute in where those zeros are that we found, and then use that as our slope for the linearization.
Right. So it's like qualitative analysis without qualitative analysis. Because this one does not need qualitative analysis, it's been solved, right? So you just take what you have and then whatever you have to say. So QA is equal to QA, so the QA of the new one is the same as QA of the old one, and so that's the beauty of it. We have all the information that we might need, and as you said, it's one point at a time. So one special point where the zeros of F, and then repeat for each. Okay, and so then, and remember, if we stay away from zeros, the behavior is generic. Okay, so in between, it's either going one way or the other way, so there are no times that can happen. So those areas are also taken care of. So local behavior then is perfectly has been described by these means. Either you do constant approximation in the generic points, or at these zeros, you do the linear approximation. Once again, the problem is solved as well. Okay, so once again, the zeros, non-zeros, that's the qualification. And then once again, that's how linearization works. In this particular case, the function is equal to 0 and above it's positive, below it's negative. Once you linearize and solve it, as you can see, there's a total match of the behavior on the left and on the right. So it's the same function. And this is what it looks like. The actual figure for the record of the linear approximation or linearization, just another word for it, of the linear differential equation. And here you are, yeah, like we are simplifying it as much as possible rather than do it like this. And speak of all these zeros of F, that's the proper way to do it. But because we're trying to keep it simple and we're doing it one point at a time anyway. So let's imagine that special point is actually, there's only one of them to worry about, and it is at 0. Okay, so just move everything to 0. You'll see that that's really in higher dimensions, even more inevitable. So f of 0 is equal to 0, and f prime of 0 is not equal to 0. So that's by the way is the worrisome possibility. What if the derivative is equal to 0? Then what happens? This is an exceptional situation. If prime of 0 is equal to 0, it's an exception when things fail nonetheless. Right? So why so? I have this example here. When it fails, here is how it fails. Okay, so so it is still possible that the derivative at that point is equal to 0, which means your linear approximation will be constant, 0. Okay, so you end up with what we ended up before, and that's a bunch of constant solutions, and they do not match what the qualitative behavior on the left. So it is always possible that we are something is equal to 0 and things break down, and then in which case you have to do quadratic approximation and so on. So that's in the back of our mind should be that it's not a foolproof solution because once again it can fail in that particular case and then produce non-matching behavior. But nonetheless, it is very nice. So that's conditional. Let me emphasize this. Once again, the special situation that's an exceptional, and if it fails, how we can fail. The only way for us to fail is like this. And then, but otherwise, we have a substitute. My differential equation, this one is substitute by that. And then just draw. You can run it with the solution is known, so you don't really have to do anything. The picture is already should be in your mind. It's always look like this. Okay, so then you know which one is plus, which one is minus, depending on what a prime is. And then, so when it's positive, we're going this way. When it's negative, we're going that way. And then it's been classified right away. So another example, here's a cosine, or rather, what is the y, cosine y. So things have become more and more complicated. So in this case, you have a function that to be differentiated, right? By y plus cosine y, that is the function to be differentiated with respect to y. That's what happened at the bottom here. And then, but then only one value that we care about. So whatever the point is chosen for us to concentrate on, we plug it into our equation. And then once again, it happens to be equal to 1 again. And we end up with the same familiar differential equation, y prime is equal to y. And once again, the behavior will be like this. Okay, so okay, time's up. Okay, so we'll just resume next time with small balls here. See you next time.